presenters are ready, maybe. Okay, let's start. I'm Sungjae Kim from Korea Tech University. This session is the multimodal system. We have 4 presenter and also we have 4 papers. And first, I want to introduce. Okay, I have at least 1 minute left, but I will stop. Okay. First presenter, I want to introduce Hong Liang Yang from Senjin University. Okay, can you go up and ready? If you, okay. So the title is MR Pilot, a mixed reality system for responsive navigation of general procedure tasks. Okay, if you're ready, you
Yes,
can
I'm ready.
talk.
Let's begin. Hi, I'm Hongliang Yang from Shenzhen University. I'm glad to share our paper here. MR Pilot, a mixed reality system for responsive navigation of general procedural tasks. This is a collaborative work with Jingzhou, Pengfei Xu, Hong Bofu, and Hui Huang. In our daily life, we often need guidance to complete tasks with complex steps, such as cooking, assembling furniture, or performing wound care. Traditional guidance methods like paper manuals often require us to frequently switch attention between reading recipes and performing instructions. This not only increases our cognitive load but can also easily lead to errors. In recent years, mixed reality technology has offered promising solutions. For instance, paper-to-place can transform existing paper manuals into spatialized instructions. Others, such as S-Air, leverage expert demonstrations to provide situated guidance. Meanwhile, projects like SR Objects focus on making individual real-world objects interactive in augmented reality. However, these pioneering works often address only part of the problem. They may rely on pre-authored content or pre-recorded expert workflow, which make it difficult to adapt to customized tasks. And while some systems make objects interactive, they don't provide step-by-step procedural guidance needed to complete complex tasks involving these objects. Furthermore, even with spatial instructions, many systems still lack true responsiveness. Users often need to manually click a button to advance to the next step, which interrupts their workflow and breaks their concentration. Therefore, our research goal is to create an intelligent navigation system that requires no pre-authoring, support general procedural tasks, and responds in real time to user sessions. To achieve this goal, we propose MR Pilot. The core idea of our work is to use large language models and computer vision techniques to bridge the gap between virtual instructions and the user's physical interactions. The workflow begins when the user describes their task in natural language and captures an image of their environment. From there, MR Pilot takes over. It identifies and enters relevant physical objects with virtual labels. Finally, the system enters the adaptive task completion stage. It tracks the user's interactions with these entered objects, providing real-time navigations and recommending the next step. Next, I will detail the core modules that make these features possible. The first core component is the Navigation Builder module. Its responsibility is to translate the user's requirements into a structured step-by-step operational guide. This module utilizes 3 large language model agents working in concrete. First, the scene analysis agent examines the user's environment, image, and task description to identify all necessary objects. For instance, to make a sandwich, it would find the bread and tomatoes. Next, the instruction dropping agent generates a natural language draft of the instructions. Finally, the task structuring agent transforms this draft into a clear structured procedure. This includes subtasks and an action transition graph that map out the logical flow of between steps. Through this module, MR Pilots achieves the ability to generate high-quality navigation for general tasks without pre-authoring steps. Once we have structured instructions, we need to connect these virtual instructions to the physical world. We use camera on the MetaQuest headset to capture the user's field of view. The image string is sent to a server and processed by an open vocabulary object detection method to identify task-relevant objects in the user's environment. Once the object is identified on the screen, we use the headset depth sensor to perform retasking and calculate its 3D coordinates in the real world. The system then overlay a virtual label on the physical object, which we called an object anchor. Of course, automatic detection is not always perfect. Therefore, we also provide a convenient manual entering interface. Users can use simple hand gestures to manually add enters to objects that were not detected by the system. Now let's move on to the action recommendation module. This module is designed to make navigation of our system intelligent and responsive. When the user begins a task, such as picking up an entered object, the system detects this interaction. This interaction is then sent to our system and processed by the action recommendation agent. This agent, based on the current task progress, uses the reasoning capability of large language model to recommend the possible next step. For example, when the users finish cutting the cucumber step, the system will recommend cutting the tomato or or preparing a sauce step. More importantly, this process is adaptive. For instance, during a step that involves waiting, like boiling water, you can suspend that step and start another one, like cutting vegetables. The system understands this action and adjusts its recommendations in real time. Then, when you resume the former step, the system picks up right where you left off. This design reduces the need for users to manually switch between steps, making the entire process more smoother and more efficient. To validate the effectiveness of MR pilots, we conduct a user study. We recruit 21 university students and compare MR pilot to a baseline system in 4 types of tasks in the daily life. The baseline system is also operated in an MR environment, but only provide a standard text-based interface similar to ChatGPT. We group the tasks into counterbalance blocks to migrate the learning bias in the later tasks. We design 4 tasks covering different aspects of daily life: making a sandwich, changing a wound dressing, assembling a toy desk, and conducting a simple chemistry experiment. Next, I will show you some result video of our system. In this task, the user is assisted by our system in assembling a toy desk using interlocking wooden components. And in this task, the user follows the system-guided instructions to conduct a small-scale chemistry experiment that generates oxygen gas from hydrogen peroxide. After the user completes 2 designated tasks, they were asked to fill in 2 standard questionnaires: the system usability scale to evaluate the user experiences, and the NASA TLS to assess the cognitive workload. First, regarding the cognitive workload, users of MR Pilot report low mental demand, physical demand, time pressure, and frustration. This demonstrates that our responsive navigation effectively reduces the user's burden. Second, in terms of the system usability, MR Pilot scored much higher than the baseline system. Users generally found MR Pilot easier to use with clear instructions and faster learning curve. Many participants mentioned that the highlight object enters help them to focus on the current task. To further validate the effectiveness of the action recommendation module, we analyze how users switch between steps. The results show that the vast majority of the participants relied on the system's interaction-based automatically switching more than 50% of the time, rather than manual clicking. This provides a strong evidence that our responsive navigation is successful and well received by the users. In summary, we introduce MR pilots and MR systems that provide responsive navigation for general procedure tasks without pre-authoring. Our main contributions are threefold. First, a flexible system combines large language model and computer vision technique that can automatically generate structured navigation for general tasks. Second, a responsive navigation mechanism that adapts to the user's action and environment, improving the workflow efficiency. Third, MR user interface for visualizing instructions and step-relevant visual cues. Of course, the current system is not perfect, with several limitations such as its dependency on network latency and constraints of the current headset hardware. Besides, low lighting conditions and occlusions can introduce performance constraints, limiting the generalization ability of the system. In our future world, we will explore more efficient object tracking methods and introduce richer visual tools, such as motion trajectories, to further enhance the user experiences. We believe that our research on MR pilots paves the way for developing more intelligent and more practical MR navigation systems, showcasing their immersive potential in everyday life, education, and training. Thank you for your time and attention.
Thank you. Is there any? Okay.
Thank you for your talk. So I have a quick question. So how do you handle the AI hallucination?
So sorry?
So typically the AI had generate the maybe inaccurate answer, right?
Okay.
How do you handle that?
If we have some mistakes in AI generates instructions, you mean that?
But you don't even know it, right? You don't even know whether that's an error or not.
Since we in our sport task, if the task is not pretty correct, the users may regenerate the instructions in the task, and also we can in our experiments we may double check the instructions, draft instructions.
So have you conduct any measurement about the accuracy part?
In our work, we didn't conduct some accuracy about the instructions. We assume that the instruction that generates is correct. Okay.
Hello, I'm Ibrahim from Virginia Tech. I don't think it would be too relevant, but I just wonder, did you ask the participants what they thought about just the system capturing the images of their environment and sending it to a server? Because a lot of time, their environment can have sensitive information as well, right? For example, if there's a credit card lying over there, it gets sent to a multimodal system that's running on a server, and we don't know what happened with that data. So did you
sorry, can you speak louder?
Yeah, did you ask participants about the privacy perception side of the system? Because the images that are being captured are sent to server and models, and we don't know how these models handle privacy of things, right? For example, if you take a picture of a scene and it has a credit card lying around, then that information gets exposed, right?
I understand. We ask the user to the user is is agree to and very willing to conduct the experiments. And the experiments is in a university public space. So the we try our best to migrate the privacy issue. And this task is like chemistry experiments. It has a standard procedure. So we try our best to migrate these privacy concerns.
Okay, thank you. Here.
Thank you for your impressive presentation. If the user enter to some environments, for instance, some kitchen, which doesn't know where is the materials, like doesn't know where is the tomato or cucumbers, your system can navigate to the user, make a trajectory to find those objects which user doesn't know.
Yes, is if the user input the task, like I want to make a sandwich, and take picture of their environment, the object detection method will
But
help
he doesn't know where is the tomato. Tomato somewhere in kitchen, and system needs to navigate you through the XR or MR to find that object. But what you present, user already see everything in the table, right?
Yes.
If he doesn't know where is the object, your system can navigate to find first and then start to make a sandwich.
If the sandwich is if the vegetables in the user's field of view, this system can detect it. If it's not in the field of view, it can't.
Some problem.
Yes,
Okay.
yes, it's a problem.
Maybe for future work you can think about it. If object is not in the field of view of user, and user is not familiar to the environment, and
Yes,
doesn't know where the object, first need to navigate with some trajectories to find that object, and then go for making something.
Yes,
This
yes.
is my comment.
And
Very
that would
nice
be,
research. Right.
yes, that would be a future work.
Okay, thank you.
Okay, it's already 15 minutes over. So this is the end of first session, first paper. Okay, thank you. Give him, yes, okay, let's
Okay.
give him applause. First, let's give him applause.
Good morning, everyone. I'm Jin Jianling from Tsinghua University. Today, I'm honored to present my latest research, SAMR, a spatial augmented mixed reality method for enhancing vision language models in 3D scene understanding. So we are at the intersection of AI and spatial computing. As my first presenter just said, the vision language models have unlocked new ways for humans and computers to interact. But here is the core challenge. How do we move from 2D visual understanding to 3D spatial interaction? Early LLM on AR-HMD used simple text queries, then computer vision convert visual text to text message. Now the VLMs process images directly, but they're still based on 2D analysis. So the question is, how do we bridge the 2D AI vision into 3D object level understanding? So recent literatures demonstrate explosive growth in the AI agent with the AR fusion research. And through our analysis, we identified three key technical trends. The first is from dataset-based to zero-shot generalization. Traditional methods rely on seeing specific datasets, limiting system versatility, and zero-shot capability enables the system to understand the process previously unseen objects and scenarios, which is crucial for real-world applications. And second is from the text level to vision level understanding. Pure text descriptions lose substantial visual details. Direct visual understanding preserves rich spatial and appearance features and significant enhancing the accuracy and the depth of comprehension. And finally, from the point level to the object level mapping, point projection only provides coarse granted spatial annotations like arrows or point, while the object level mapping achieved precise 3D boundary localization and semantic understanding. So based on this analysis, we try to propose the SAMR framework to achieve 3 critical technical breakthroughs. The first is zero-shot object level segmentation. We achieve real-time object segmentation on AR-HMD without pre-training, and it's object level, so it's good for the VRM and on the HMD. And the second is comprehensive 2D to 3D VRM pipeline. We have constructed a multi-scale feature fusion mechanism for the pixel level to object level to achieve a deep integration of visual and spatial information. And the third is natural interaction, and users don't need to complex descript queries. They just select and ask the questions. The system automatically understands the user's intent based on the spatial context they choose, they select. And so SMR gave us 4 main spatial intelligence capabilities for the real-world scenarios, like target object selection. You can just simply select the objects in a new scene with your hand or eye. And the spatial relationship reasoning, it understands how the objects relate to each other, like what is next to what and what is the distance between 2 objects. And the questions without modifier, you don't need to add extra description of locations or appearance of the objects you asked. And the cross-based query, you can move around and query it, it remembers what it has seen. To do all this, we only need our AR-HMD like HoloLens 2 to do. So let me walk through the SAMR actually work. So we designed a unique zero-shot object segmentation approach. The core innovation is using the FastM to obtain the object mask and the grid UV coordinates. We captured the first-person view images through the HMD and targeted real-world scenarios while recording the camera parameters. Then we uploaded the images to the cloud for processing to ensuring the fast response times. And we employ a FastM model to perform zero-shot object level mask segmentation on the image. And then we apply a uniform grid sampling on the uptime mask to generate the grid. Yes. To this point, we focus on the 2D images processing, obtain object level mask, and service 2D grid points. And next, the points is not useful. So we implement the crucial 2D to 3D mapping to obtain object level meshes, which is the fundamental for our 3D interaction. The core concept is recasting on the same mesh for generating object level mesh. Based on the camera parameters, we constructed the spatial position for 2D images and calculate the projection rays for each point, and generating rays from camera position to the same mesh and detecting collision points is for all the points on the images. So we get the point cloud of the object on the scene, and which result to the 3D mask of the object. However, to object these points cannot collide to the user's rays or user's interaction intents. So we need to generate the mesh for the 3D points. So previous traditional simple triangulation or the mesh generation method can be problematic with this problem. The 3D point projection generates significant noise. Like you can, it's not always be accurate. So you have to do some thing to deal with it. So therefore, we introduce a spatial hashing algorithm for the neighbor point filtering to eliminate the neighboring points that would affect the final mesh qualities. So as demonstrated in these videos, our method work in real scenarios with real objects with any pre-training on the specific datasets. It's based on the VLMs and also the FastM models. With just a single photograph, we generate interactive meshes for objects on the desktop, and the meshes can collide with interaction intent rays, like your hand rays or your eyes gaze rays, because it's a collider. And we also support various visualize modes like bunny box or just arrow to it. So we have tested our system across diverse scenes and objects to achieve excellent mesh qualities. We have also evaluated scenes with varying objects counts, like from 5 to 20 or even more. But with 5 to 10 objects, it performed the best. And for the accuracy is required for the use. And as shown here, we achieve accurate object labeling and object mesh generations. And we also design an interactive human-computer interaction interface supporting multimodal interactions like hand-following AR mats. It can control all the interactions and also show the users words and what the answer to their questions. And we also design the hand gesture raise and eye gaze raise, so users' questions for the VLM are captured through voice-to-text description through the cloud service. And after implementing the AR-based user queries and object selections, effectively transmitting user select objects and questions to the VLM, representing our big innovation. And we have designed the VLM integration pipeline for the object level encoding and decoding. First, our object level encoder converts user select objects into a list and generating augmented annotated images with numbers on the original image. So the user's text questions are compiled into a generated prompt. Critically, this prompt has specific output content and format requiring a JSON format. So the VLM processing, and we obtain the JSON format text answer from the AI agent, and which our system can automatically process into two components. Like the first is the object data information list, including object ID, category, or name, and also the answer to the user's question specifically. So let's see what the system can
What
do.
is the
Based on this
relationship
framework,
between
we
these
have
three
achieved
objects?
numerous exciting AR and AR functionalities, especially validate in real-world scenarios. First, selecting three objects and querying their relationship in the scene. In this case, the VRM identifies them as the VR headset and controllers, so generating the corresponding 3D spatial name for each object. And second, our system enables
the
2D
distance between
VRMs to
these two
perform
objects?
3D spatial analysis. For example, measuring the distance between a shelf and a screwdriver on a desktop, we intentionally place 15-meter rulers on the centimeter rulers on the table, so to be the reference, and the response is remarkably accurate. This enables traditional VRMs to function effectively in 3D AR HMD environments. And
What is
third,
this
when
painting
facing
about?
multiple similar objects, like 4 paintings, our system accurately responds based on the user selection. So it shows how selection is important. When you're facing something familiar, you can ask a question just like this painting, not rather than the leftmost painting or the painting looks like blue or something descriptive description to tell what you are asking. You just select. The fourth, we support context-aware
Can you show me
queries.
the painting by
After
Vincent?
identifying 4 paintings, we can ask of the VLM, which is the works by Vincent van Gogh, and then it can generate the appropriate AR indicators. For most of the time, is like the arrows to guide the users where the painting
The
is.
work by Vincent is
So finally, we can tackle the challenge task of cross-spatial context queries. For example, we can ask which tools to use to
unique
assemble
the
a mechanical
screwdriver
product on
and
the table.
pliers
The
to
VLM
fix
can
the
analyze
nut.
the real environment in real time and generates accurate AR indicators like the arrow to assemble the nuts you need the wrench or the screwdrivers on the other side. So we present SAMR, and we welcome collaboration with colleagues that also interested in AI and AR integration. And at the end, as a small bonus, we also have the SAMR. You can look; it's very familiar to ISMAR. So thank you for your attention. That's all.
Here.
Thank you for the great talk. Do you expect your system to work with transparent or semi-transparent objects?
Maybe transparent objects. Am I understanding right? Maybe transparent objects, if it can be recognized by the latest AI agent models like VLM models, I think it can be adapted to our system because this is a framework that can bring the VLM into our system, so it can upgrade maybe next day or even few days later. Because if the VLM improve, our system ability will improve. And we mainly contribution is focused on how we bring the VLM capability into our system. So I think that transparent objects right now can be identified in by the VLM or the latest AI agent. So maybe I need to try it in my test later.
Do you have a repository?
Yeah.
Repository with your system. Can we try it out?
Sorry, I didn't get it.
Do you have your code in
Yeah.
a repository? Can we try it out? Is it available?
Yes, I think that our code is open source, so everybody can try it. So on their own things or their target.
Thank you.
Yeah, great. Thank you for great talk. My question is, how about is your system can deal with like dynamic object or dynamic movement on the 3D world?
Yes,
Like, yeah.
I think that is the common problems for the AI agent and AR. So right now, our system can't deal with the fast moving or dynamic objects because if it's dynamic, you need to take another image because we are analyze it based on the images that users queries and ask, like the original paradigm of how we use the VLM nowadays. But if we take videos of the whole process, maybe we can dynamic analysis with the moving objects, and that will be the future works maybe for all this field research. Thank you.
Fantastic work, great stuff. So you show this capability of measuring distance between objects, right? How accurate is that? Because VLMs are known to be not that accurate in that.
Yeah. So this method is achieved by the first of all is our object level segmentation. If we have object level segmentation of the objects, we can get the center, the boundary of this object. So we can send the information, the data of this object information to the VLM, and it can calculate to your questions like the distance. So the calculation is tested, is calculated on the cloud by the VLMs. So it's not algorithm we design, it's automatically calculated by the AI agent. So maybe the accuracy, I think, is depends on how accurate of the position that you set, you build your object level meshes. If it's correct, the center and also the boundary is correct, I think from our test that the ALM, the VLM, the AI agent, they can do the correct calculations.
Okay, we don't have enough time. Okay, let's thank our presenter.
Hello, everyone. I'm Ma Qixiang from Beihang University. Today, I'm excited to share our work, SGSG through guided 3 scene graph generation. This is together with Fan Runze, Zhao Lizhi, Wu Jian, and Wang Lili from Beihang, and Ying Soukei from Moscow Polytechnic University. So, scene semantic graph describe how objects relate in the scene. The field has evolved from 2D to 3D, enabling many embodied intelligence applications. Yet, current 3D scene graph still lack an intuitive interaction way to refine predictions for fine-grained tasks. With the growth of XR, users can draw 3D strokes to express intent directly in the space. By combining XR strokes with 3D scene graphs, we can perform interactive corrections, much like interactive 2D image editing. Early 3D scene graph method began with the 3D SSG, which encoded the instance segmented point clouds and propagated the feature through GCN. And later, SGFN handled coarse point cloud patches, and fused them into stable semantic graphs. In 2023, joint SSG aligned 2D keyframe features with 3D point clouds, enabling incremental sparse RGBD scene graph generation. More recently, Open3DSG in 2024 distilled the vision pre-trained model into the encoder and used the LLM-based Q-former queries to prototype open vocabulary 3D scene graphs. XR edge devices capture coarse, noisy point clouds, causing semantic fragmentation, predicate ambiguity, and label mismatches with the traditional scene graph generation method. To achieve accurate user-guided generation, we must overcome these challenges. First, design a controllable guidance that affect the prediction. And second, inject the guidance into smoothly into the inference. And third, generalize the local corrections to improve the whole graph. Our SSG pipeline takes a derived geometry and 3 stroke types as an input and output a refined 3D scene graph. It has 3 steps. First, guidance representation captures user intent from strokes. And second, guidance injection blends it into inference for local and global correction. And third, the semantic inference applies extra intervention losses to enhance accuracy. In the first step, user strokes are processed through 2 pathways. The upper pathway extracts the temporal features using an attention-based encoder to capture stroke order, directions, and pauses that reflects user intent. The lower pathway encodes geometric attributes to describe a spatial form. Combining both of them helps clarify strokes into 3 interaction types for richer representation. We define 3 interaction types that, as shown in the yellow zigzag, blue line, green circle, respectively. Type 0, strokes can brush large objects to merge fragments. Type 1 can link 2 parts to correct predicates. And type 2 can circle unclear object to hint missing nodes. In step 2, stroke features are aligned into a shared guidance space. For type 2 stroke, the auto-encoded point clouds inside the circle area is also included as part of the guidance feature. Then the guidance is injected into the inference network in two ways. First, strong guidance injection directly located the target geometry and blend the features. And second, weak guidance injection performs a global similarity search, updating other regions with a similar feature or errors pattern. Here, alpha and beta represent the strong and weak injection rates. Our method enhances semantic embedding clarity. It better separates some large objects and cluster semantically related objects. Even similar scenario items become more distinct in feature space. Ablation shows smaller injection rates improve fast with more strokes, while large injection rates reach higher accuracy but saturate due to added more noise. The third step, semantic inference, is built on a point cloud encoder flow by a GN-based message passing. The trained losses have 2 parts, core losses and intervention losses. The core losses include classification loss for type indicator, autoencoder, and the scene graph, and alignment losses for the 3 projection heads. The intervention losses further include consistency, repulsive, and geometric constraints. They encourage type 0 to keep patches semantically consistent, type 1 endpoints to internally consistent but mutually distinct, and type 2 to separate foreground from the background features. The label of planar or vertical objects or some contacting predicates are guided by geometric rules. After applying intervention, node predictions concentrated along the diagonal, and the spatial hierarchy predicates are also improved, while mismatched in the non-category becomes much less frequent. Before implementation, we collected a small set of user strokes and augmented it to about 2,000 samples to train a guidance type classifier. It achieves good accuracy and validated the representation ability of step 1. Here we show several runtime examples of our method. They demonstrate that the XR strokes intuitively and interactively improve the scene graph accuracy. The system is also sensitive to different stroke type of user guidance. Each type plays its own role in refining the scene graph. To train our pipeline, we build a stroke dataset on top of the 3D scenario dataset 3R scan using a heuristic generation method. Each stroke stores its points, type, target, label, symbol, numbers, and length with parameters fitted from the preliminary experiments. Here we show several correction results. In the park scene, a type 0 stroke fixed the hot wall. A type 2 stroke identified the table and separated the distant parts. And a type 1 stroke corrected the standing on predicate. In the bedroom, type 0 and 2 strokes corrected the bed and cabinet, while combined interaction generalized the relations such as wall attached to floor. The upper table shows performance across the methods and the metrics. Our method outcome SGFN on all accuracy measures compared with the multimodal joint SSG, which added 2D visual inputs as assistance. Our performance is comparable overall, and we achieved higher predicate accuracy and precision. Ablation shows that adding points in normalization, spatial features, intervention losses, and loss fitting slightly lowers recall, but increases top 1 accuracy and precision. We compare our method with 3 sorter methods. With the cross-model method joint SSG, style semantic error occur, shower curtains are mislabeled as curtains. And due to occlusion in 2D assistant input, some supporting predicates are mismatched. With SGFN fragmented point clouds performance suboptimally after semantic fusion, the toilet is mismatched. 3D SSG, which lack reasoning aggregation, shows even larger deviation. Our SSG, guided by user interaction, successfully corrects mislabeled, mismatched label, merges scattered parts of large curtain objects, and shares corrected stylized objects across the scene, from toilet to shower curtain, while also achieving better global predicate propagation. We conducted a user study where participants navigate the scene, corrected the semantic label using neither hot correction or our stroke guiding approaches. Our method required fewer interactions, achieved the shorter task completion time, and result in a lower post-error rate. Using 4 NASA task log dimensions, participants also reported a lower cognitive load. Sorry. Each interactive update round include communication, inference, calibration, and rendering. Average end-to-end latency is about 262 milliseconds. The heterogeneous architecture ensures uninterrupted real-time interaction after scene or network are loaded. Errors from one stroke can be fixed by later round. In the second round, a stroke on the wall mislabeled the coordinate, but later circling the coordinate corrected both its label and relations decoupling from the background. The fourth round strokes further showed the global generalization. So in conclusion, we proposed the SSG. It integrated stroke representation, guidance, injection, and intervention losses to improve accuracy and generalization. Our approach enhances scene understanding with the structured semantic information for downstream XR application. In the future, we plan to extend it beyond stroke-only input, enrich SG stroke dataset, and handle dynamic open-ended scenes for broader real-world application. So please feel free to scan the QR code to connect. Our implementation repository is under preparation. Thank you very much.
Thank you. Is there any question on the floor? Okay, I have questions. It's a technical questions. Technical questions. You have many losses when you're training in previous slides. So how did you balance the many losses in your training procedure? I saw.
Yeah, that is a good one. It's a bit
semantic loss.
like here. Oh, sorry, it's very far away from that. So we set some weighted parameters between each terms of the losses term, and based on our experiment, based on my memory, it's the first one is 0.3 and the second one is 0.7.
Yes.
But in our interface, the parameters can be changed during the training.
Yes, that's right.
So we can pick the best one model as our implementation model. But I know it's sometimes simpler is greater.
Okay.
Yeah, maybe in the future we can try some less term losses function.
Yeah, that's good. Thank you. Excuse me.
Fantastic work, great stuff. So you collected lots of feedback from your users in the user study. You collected, there's information about how much faster users do their tasks and all of that. So what was the qualitative feedback from users like? Did they identify any opportunities for improvement?
I didn't get the second part.
So
what user feel doing the...
So you tested the system with users and you saw that it's effective. Did users tell you what they want to be different? Did they identify any opportunities for improvement?
Yeah, actually, I want to mention this. Two of my coworkers during the user study, they didn't draw the stroke as my interaction paradigms. They draw on the surface of a chair or a table. They just draw the skeleton of the table. So that is, as I mentioned in my PowerPoint, is one of our limitation. We just using some limit stroke patterns, which generated from heuristic strategies. So maybe in the future, we can use some adversarial the generative strategy to include as much as possible stroke pattern to feed or generate for each user, every user. Thank you very much.
Impressive presentation. Regarding the extending SGS protocol, when the user wants to dynamically update 3D scene in the mixed reality environment for some sort of extension of SGS protocol, what do you think? Did you do anything? Dynamically update 3D scene when the user interact with object in the mixed reality environment? Is that Thank you.
Yeah, thank you. Thank Okay, please welcome the presenter.
All right, what about now? Better? Yeah? Okay. So today I'm presenting multimodal classification of student distraction in educational VR environments. Basically, this is like how we came up with the idea of this, I guess, this experiment. Virtual reality has enormous potential for education. It's immersive, it's interactive, it's more engaging than learning in a traditional classroom. But with that immersion comes a challenge, and that's difficult. And it's difficult to know when the learner's attention drifts. In a physical classroom, a teacher can pick up subtle cues, eye contact, body language, to determine if a student's distracted. But in VR, we don't really have that capability. So we wanted to create a way to determine distraction in a VR environment, in a network VR environment. The original idea came like during COVID when there was a lot of distance learning, and in our VR classes that we taught, we were brainstorming ideas for how can we still have live classes and interact in VR. And so we're thinking about like creating classes in like VR chat and stuff. But that brought like network issues, things of that nature. So this is just like the research gap. Most VR distraction studies define distraction based on external events, such as the phone ringing or giving them a secondary task, like an end-back memory task. These events make labeling easy because researchers can assume distraction occurred when the intervention did. But that assumption oversimplifies what distraction really is. And that is, it ignores cognitive distractions. Moments when learners lose focus, they zone out, or they're starting to have mind wandering without any external trigger. As a result, much of the literature captures when a distraction was presented, but not when occurred. Our work addresses that gap by expanding the definition of distraction to include both external and internal lapses, recognizing that attention loss in VR can arise even in the absence of obvious stimuli. Related works, distraction is a brief involuntary lapse of attention. It's distinct from divided attention, where people are normally asked to split focus between tasks. In much of prior work, that distinction isn't always clear. Many studies rely on measures developed by other cognitive states, things like mental workload, fatigue, drowsiness, because there's validated surveys, like the NASA TLX and stuff, that are easy to determine and like they're correlated mental states. But I don't think that's like the pure definition of distraction. The result is that distraction often gets approximated by these related constructs. Our work tries to separate them, focusing specifically on unintentional lapses of attention, whether they're triggered externally or arise spontaneously during VR learning. More related work, there's a lot of studies out there that try to determine cognitive state, not just distraction, and they use different physiological sensors. EEG, eye tracking, heart rate, head motion. EEG captures rapid neural activity, but it can be very noisy. Eye tracking adds gaze and pupil data, while heart rate and head motion reflect effort and arousal. Each offers useful but incomplete information. So we combined them to build a fuller picture of distraction in VR. So we had 4 research questions for this paper. The first is, how well can a real-time capable model can detect distraction in VR, essentially testing whether it's even feasible to identify distracted states as they happen. Real-time being the definition of not doing post-hoc processing, independent components analysis, z-score normalization under pre-processing and things like that. Well, you can still do z-score normalization, but there's like a running model you have to use. Resource question 2 explores the model configurations that are most effective. Things like network depth, epoch length, regularization, overlapping windows, etc., to understand which design choices matter for distraction detection. Research question 3, we're extending the binary classification model to a 5-state model, I guess. And we're doing this by having undistracted, cognitive, real world, so external distractions like someone's knocking on your door, your cell phone's ringing, VR auditory, which is like distractions that emanate from the VR device, and VR visual distractions in VR. Research question 4 focuses on interpretation, which physiological features contribute the most to detection, and what that tells us on how distraction manifests in VR. So this is the study design. The interventions in the study provided control opportunities for distraction, but an external trigger does not guarantee that distraction actually occurred. Sometimes participants ignored the event entirely. Other times the disruption might have caused distraction, but not in the way that we'd expect. For example, a phone ringing might prompt a participant to think about something unrelated. That would be labeled as a cognitive distraction rather than reacting to the sound itself. The distinction is important because it shows that distraction in VR isn't always bound to the event that triggers it. This is why we relied on self-reports as the ground truth to capture whether distraction was experienced at all, and if so, whether it was driven by an external stimulus or by internal self-guided thought. This framing helps treat distraction as a subjective cognitive state rather than a guaranteed reaction to environmental change. So we had 34 participants. We had at 40, but 6 we ended up rejecting. And this just kind of outlines, what the participant went through during the study. I wish I had a video for this next slide, but this is just a picture of the VR environment in which they experienced. It's a physics-based lecture where they learn projectile motion. So they went through like a guided lecture where we showed them in VR, the arc of a projectile with the different features of force, angle, and gravity, and how it affects the motion of the projectile or the cannonball as it goes through. In addition to that, at the end of the lecture, they had a gamified task where they had to shoot the cannonball to hit a target as many times as they could within the time limit, and the target would move randomly every time they hit it. So to elicit the state of distraction, we came up with different interventions. 9 were used to potentially evoke this mental state. Some came from prior studies. Others were designed by our lab to reflect realistic scenarios in remote VR learning. Things like phone alerts, echoes, and brief visual glitches. In this study, each distraction lasted for about 5 seconds and served as a controlled opportunity to observe distraction without forcing it. So this is all the sensors, the physiological sensors that we are gathering when we're creating this data labeling. We recorded data from 5 synchronized sensor modalities: EEG, eye tracking, heart rate, headset motion, and controller input. EEG captured the neural activity across 16 scalp locations. Eye tracking provided gaze, pupil size, and blink data. Heart rate and heart rate variability reflected overall arousal. Motion and controller data captured physical engagement. All streams were synchronized to Unity's 90 hertz update rate. That's a limitation of the VR device. We're capped at 90 hertz. I think you can, oh, I'm not gonna get into that right now. So everything was aligned frame by frame. When samples were missing, we forward filled the most recent values and applied z-score normalization for standardization. Beyond basic filtering and frequency composition, we kept pre-processing minimal, no interpolation or record removal to preserve signal integrity and ensure real-time visibility. So we tried to keep the data processing to an absolute minimum because we're definitely targeting real time. So the raw data that we get from the devices, we're feeding into the machine learning model other than maybe getting the EEG frequencies. The resulting features from each modality were segmented into short time windows and fed into an LSTM-based classifiers for distraction detection. So this is the results of the binary model, the binary classification, detecting whether participants were just distracted or not. We tested several hyperparameter combinations, suggesting window size, dropout, attention, regularization. These various variations led to slightly different F1 scores and confusion matrix patterns. The best model was a 3-layer LSTM with attention, reached an F1 of 0.873 and an AUC of 0.73. Overall, the model performs on par with other distraction classifiers and other papers, but this also detects cognitive distractions and is real-time capable, making it more adaptive for VR learning systems, real-time VR learning systems. You can see there's a bit slight bias here where it is detecting distracted. This is the 20 best indicators of distraction from the data we collected. We used the SHAP analysis to understand which features the model relied on most. EEG emerged as the strongest predictor, particularly activity from the parietal and occipital regions from the delta, theta, alpha, and low gamma bands. Eye tracking features such as gaze origin, direction, and pupil size added behavioral context, while headset velocity along the z-axis, that's small forward and backward movements, are also contributed. Together, these results show that the distraction in VR isn't captured by any single signal, but by a combination of neural, ocular, and motion cues. I color-coded the source of the physiological sensors on the right, where you can kind of see that EEG and eye tracking both combine pretty heavily to create this machine learning classifier, or the accuracy, that F1 score. For the results of the multi-class model, we extended it again to undistracted, real-world, VR auditory, VR visual, and cognitive distractions. This is from the user feedback. So it's not just the interventions that we use to elicit distractions. This is the self-reported distraction states, that distraction sources that they wrote down in the survey. The model achieved an F1 score of 0.328, which is well above like the 20% like random baseline for the 5 classes, but it's still pretty low. So we still have a lot of work to do on making this a little bit better. Most of the confusion occurred within distraction types. You can kind of see, maybe you can, it's kind of small, but the undistracted state is still getting pretty high accuracy. It's only when we're trying to create the classifier of distraction, trying to determine the type of distraction within distractions where like the confusion is. And they tend to be misclassified as VR visual. This suggests that the model captures the presence of distraction but struggles to distinguish what kind of distraction, since physiological responses can overlap. The best configuration, like in the binary model, was a 3-layer LSTM, consistent with what performed best. Overall, these results show that multimodal data supports fine-grained classification, but the boundaries between distraction types still remain subtle. Limitations. While the results are promising, there's several limitations to keep in mind. First, our sample size of 34 participants from a single session limits how broadly these findings can generalize. The data set is somewhat imbalanced. We had far more examples of external distractions than internal cognitive lapses. The equipment, the environment itself, the experiment itself was highly controlled. A short 15-minute VR lecture with predefined interventions. Finally, the gaze features, we only did the raw gaze features that we got from the device. In the future, we would like to incorporate fixations and saccades to better capture visual attention. So the main takeaway of this experiment is we created a very good classifier that competes with all previously published work, not better or worse, is middling, but we're doing this in real time. We're doing this with almost raw signal data, and our broader definition of distraction does include cognitive lapses. For future work, we're going to do balanced data sets. We're going to rerun the experiment. We're going to do richer gaze features, more varied VR environments, more interactive VR environments, and we're going to deploy it in real time to see how well it occurs in like a real classroom. Questions? Thank you.
Okay, any question?
Thank you for a great job. I would ask if the movement of a headset will bring extra noise to EEG.
Can you repeat that?
Will the movement of headset bring the extra noise to the EEG?
Yes. During this study, we wanted to have ecological validity, so we didn't actually constrain the participant from not moving. Usually in EEG experiments, you tell them not to move their head at all. For this one, we wanted to simulate a real classroom as much as possible, so we didn't give them any instruction. They could move their heads as much as they wanted to, which did increase, it led to the reason why we had to throw out 6 samples, because I guess the connection to the EEG, certain spots in the scalp, it wasn't good data, so we just threw them out entirely. Did that answer your question?
Yeah, 16 channels of EEG is enough for your work.
That's what we had available. I would love to do one with a more what is that called? I'm drawing a blank, but you know what I'm talking about. The EEG cap, one with more channels, with a higher frequency rate, some stuff like that. But we just used what we had available to us.
Thank you. Thank you.
Can I ask a question? Okay. First of all, thank you for a great talk. It was very interesting. I have 2 little questions. First, did there any kind of self-report that the participants report that they're actually distracted or not?
Yes. During the study, we separated the VR lecture into 13 segments. So each segment was about a minute in length. And at the end of each segment, which was generally a break in the lecture from moving from like one topic to another, like gravity to force or acceleration, we stopped the lecture and we asked them questions about what they experienced. Were they distracted? If they were distracted, what was the intensity? What was the source of distraction? And the source of distraction is not guaranteed to be what distracted them. So we left those questions open-ended so they can actually respond as much as they could. And then we went back and labeled the data.
Okay, thank you. And the second one is, most of those distraction cause is more of an active distraction, right? Do you also considering some passive distraction like boredom or like sleepiness?
Whatever the respondents mentioned is what we like the passive distractions. If they mentioned that they were bored, or if they mentioned that they were mind wandering, we definitely recorded it and labeled it as a cognitive distraction under like one big umbrella. But that is something to consider in the future, is to be a bit more fine-grained for the cognitive distractions.
Thank you.
Okay. I think we need to. Okay. Thank you for the presenter, and give him an applause. Okay, I think it's time to close our session. Thank you for the presenters and active participants. I'm sorry, the session is a little bit delayed, and please enjoy the rest of the ISMA 2025. Okay, thank you.